Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm going to get this thing started. I have some announcements to make. And first of all, welcome. Thank you all for coming. I know people are probably, since we have a lot of locals folks, people will be streaming in as they fight the traffic. But I hope we still have a good crowd already this morning. That's great. First of all, critical announcements. We've got the breakfast as it is back there. Those of you that are unfamiliar with this room, the facilities are out the door around the corner, so it's just on the other side of this wall. We'll have a demo fest this afternoon. There's about 5 demos I think we've got scheduled, and that's going to be right out in this lobby out here. That'll be at 4:30. And then tonight there's a reception. After the demo fest is done, we will go over to the reception area, which is called the Spitfire Grill at our Commons. It's a short walk from here, so if you're parked, you don't need to move your car or anything like that. And I have a map to show you later how to get there. First of all, if there's any questions about anything going on here, you can ask one of our team. Dan is here. There's Dan. Vanny, is Vanny here? There's Vanny in the back. Wen Ming is here. There's Wen Ming. And let's see. Oh, we got Harold. I don't know if Harold is in here yet. Nope.
Clocking in.
He's clocking in. Okay. Kenji's there. There's Kenji in the back. Okay. And Kristen is right there. And me. I'm Dennis, by the way. So this is being live streamed, and so I wanted to let anybody know that those of you that are compulsive tweeters, and especially people that are viewing this live, if you want to tweet comments, feel free to do so. We have people here that will be monitoring the tweet stream, and so it's #eScience14 is the hashtag. There's also, we have this LinkedIn group, Microsoft Azure for Research. And so all you have to do is, if you want to join that, please go on. Now, it's my distinct pleasure to introduce our keynote speaker. Raghu Ramakrishnan he's an important pioneer. Yeah, some of you noticed, Bing is wonderful for getting pictures. And so we've got pictures of Raghu through his career, from being a young assistant professor to being a vice president at Yahoo, to being a thought leader at Microsoft. And so these are the stages that we see in his career so far. But he's a pioneer in the area of deductive databases, data mining, exploring data analysis, data privacy, web scale data stuff, lots of data stuff. He PhD from Texas. He's an ACM and Packard fellow. He was a professor at University of Wisconsin-Madison, vice president and research fellow at Yahoo. And now he's a technical fellow here at Microsoft. And so, Raghu, I'll let you take it away. And someone's going to automatically change this. There it is. Great.
Thank you, Dennis. So, as I told Dennis, I'm actually grateful he chose not to use the photo with a jacket. Alrighty. So today I'll tell you about big data in general. But this won't be so much a talk about Azure. It'll be more a talk about the field as I see it and how it's evolving. Here at Microsoft, I actually now wear 2 distinct hats. One, I head an applied research group called CISL, Cloud Information Services Lab. And I also now run the engineering for the big data teams, right? So one leg on both sides, I guess. Let's get going here. So when thinking about this buzzword, big data, what is it really? I think the best way to wrap your head around it is by thinking of what it lets you do that you couldn't previously do. Okay. So I'll begin by giving you a quick overview of a few applications. And I'm just going to choose some examples I worked with at Yahoo. Time permitting, I'll say a little bit about other things. But I'll then segue from that into the tools that enable these kinds of applications. And that will take me to where I believe the frontier is shifting. So if you take the tools that have taken us thus far, Mapreduce, and things that build on Mapreduce, what next? Right? And I'll try and give you a glimpse for some of these. The very last part of the talk, time permitting, will be about a project called Reef that we have been working on here that we just contributed to open source. It's designed to work with things like the Yarn Resource Manager in the Hadoop ecosystem. So Microsoft is now pretty heavily involved in the Hadoop open source world. Okay. Great. By the way, if you have questions, just put up your hand, we'll talk. Don't hold your questions till the very end. I'd rather talk with you than at you, so feel free. Let's look at the applications. So one of the first things I worked on at Yahoo was this project called Web of Concepts. And over time at Yahoo, it formed the basis for a product effort called Web of Objects, or WOO. And similar things are there at pretty much all the web companies. Here we call it Web of Things. At Google, it is the Knowledge Graph. Same thing at the end of the day. The web used to be this collection of pages. And search was defined as finding those pages that were closest to your search term by some measure such as TF-IDF, modified in various ways. Today, the game has shifted. Today, the expectation is that when you ask for Mumbai, you want information about the city, right? So users think in terms of concepts or tasks, and the game is to understand their intent at roughly the level that they think about it, and to present web content that is suitably packaged. So conceptually, you want to organize information about the web, information found on the web, around the concepts that you think people care about, right? So everything about Mumbai is together, not organized by the page where it was found, but pivoted rather on the concept. That's basically the idea. And an index here would be not so much a token-based index, but something that's concept-based, okay? As examples of what this would give you, if you go search for Julia Roberts or pretty much any celebrity, all the search engines will give you some variation of this page. The most important thing to note is the vast majority of the real estate is based on content that is somehow in a database that's been put there by retrieving information from all over the web, scraping it, massaging it, getting feeds, and then splicing all this together. The organic 10 blue links that you're used to, this is the first of the blue links. The rest of it is down there below the fold, okay? So whenever possible, you'll try to present this kind of a result. Why? The click-through rates are much higher, okay? The information here is pretty much on the web. What's different about this search result is you have synthesized, you have aggregated information about the concept in question from many different places, presented them once. Of course, if they're talking about Julia Roberts, their sister-in-law, there's a bit of a problem here, right? So figuring out what they mean when they type in a keyword, the true concept, this is tricky. So when you're not sure, you present the 10 blue links, right? You only present something like this when you're really, really sure you know what they're looking for. And part of the way you get to be sure, you use your understanding of the content to present all of these refinements of what they just typed in, okay? And if they click, then it's a reinforcement that you indeed guessed at what they were looking for, okay? So the work on organizing the information on the web pays off in two distinct ways, helping the user navigate or helping you understand their intent, and then delivering the payload, the actual aggregated search result. All right, as another example, if you're looking for idli restaurants near Ann Arbor, idli is a kind of South Indian, whatever, puffed rice cake. The way this is put together, you crawl the web, you classify pages as restaurant pages. Within there, you classify pages as menu pages. Within there, you extract terms that refer to various kinds of food. And you build an index with each restaurant recognize that you already know that this is a restaurant, a concept. And then within that, you're looking for entities that are menu items. And now you're building an index on a combination of restaurant and menu item, right? So now when a user clicks and says idli near Ann Arbor, they're actually going to get restaurants that have idlis in their actual menu. The menu contains this term. Okay. All right. Especially as you shift to form factors like mobile, where space is at a premium, using the real estate to deliver highly dense information is critical, because people don't want to scroll. Let me give you another example. Content optimization. If you take the front page of Yahoo, traditionally it's been curated by editors. Every link you see there is manually placed by an editor. I should say was. Today, virtually every link you see is placed there by some algorithm at the point that you click on it, on demand. This shift, this is something this is another of the projects I worked on while I was there. Let's talk about this set of 4 links in particular. This is called the Today module on the Yahoo front page. This is the same. The choice of which is the first link and which are the 4 links you show is the game. Underneath, there is a pool of about 100 links that you could show. Editors curate that pool, but the algorithm selects what to actually show. The difference in doing this is enormous. The click-through lift by doing this was over 300%. Okay? And financially, that translates into many, many zeros with a significant leading digit. Okay? So today, over, I don't know, in the high 90s, 90% of all Yahoo traffic goes through pages that are fully optimized in this sense. What does this really take? Right? On this page itself, most of the links are algorithmically selected. What does it take to do things like this? Let me go into a little bit more detail. You take all the articles. The first time you see them, you have no clue who's likely to click on them. So you go by doing content analysis. You analyze the articles offline. You look at the historical performance of similar articles. You fit machine learned models. And so you have an a priori estimate of click-through for a brand new article. Then you use this to have prior probabilities in estimating the click-through rate when you show this to a certain kind of visitor. You refine these estimates using online statistical explore-exploit algorithms. Okay? These are so-called bandit algorithms based on slot machines. But the idea is, when a new article is, when you have an article, you show it to someone, and they either click or they don't click. If you show it enough times, you have a pretty good estimate of the probability that the next person is likely to click. However, there's a delicate trade-off. The articles decay. They are time sensitive. You have a few hours, right? In those few hours, if you spend all your time estimating the probability, by the time you have a really good sense, it's irrelevant. So you want to spend the vast majority of your time exploiting the most popular articles, while at the same time parsimoniously exploring to figure out which articles are growing in popularity, which are shrinking, which are indeed the most popular at any given instant in time. And the mathematics of how to blend, explore, and exploit is what the statistics behind this is all about. The engineering behind this is a different kettle of fish. You have to show articles to people around the globe on tens of thousands of servers, take the results of something that happened in Shanghai, feed it into your modeling servers in Sunnyvale, and the next person in Singapore, right, is influenced by what the person in Shanghai did. Now, the butterfly in Brazil, it's real. Okay, so if you take what it requires to do all of this, I'm just going to put up names of some systems that are underneath this. Hadoop. We use Hadoop for everything from the actual queries to extract and analyze the summaries through the data pipelines. Getting enormous amounts of data gathered in one location on the globe and then move quickly to other locations on the globe. End to end, from the person in Shanghai to the person in Singapore, it's about 10 minutes. data streams, pipelines, NoSQL stores, all of these things that you think about as quote-unquote big data technology boils down to one thing. You have databases operating, doing the things that databases traditionally do, large-scale queries, large-scale CRUD workloads, right? But now at web scale, right? And some of the criteria, how important is it to have fully serializable transactions? What kind of availability demands do you have? These knobs have been changed in significant ways to where a brand new generation of architectures has come into vogue. So let's look at that for a moment. What do I mean by web scale? By the way, the first example on the Web of Concepts, hopefully the point there was clear. Although I didn't put up a slide showing the underlying infrastructure, you simply cannot build that kind of information extraction at web scale without using technology like Hadoop, Peanuts extensively. Okay. What do I mean by web scale? Here are some numbers. I'm not going to talk to them in any detail, but basically 100 billion emails a month, okay, geo-replicated across a dozen zones. I'm just going to say very, very, very conservatively, 10,000 plus servers, right? Millions of reads per second of a given page. Visits in the order of tens of billions, right? Ad serves, ad impressions, same scale. This is orders of magnitude larger than the largest enterprise databases have historically been. Well, it's going to be dwarfed within a few years by what we are going to see from yet another class of applications, the Internet of Things. And this encompasses not just things like websites. It's going to seep into everything you do, right? Biology, environmental science. It's all potentially going to be transformed by the ability to embed sensors of every stripe in everything you do. Your ability to observe is going to be unparalleled. The fundamental difference between a website and a traditional application like, say, Word is observability. If someone sneezes on a web page, I know how long and how loud, right? And that's what I can react to. That observability is lacking in a package application running on your desktop where no one can view it. Of course, some of you are thinking Office 365, no doubt. Yes, we can watch you sneeze. And that means many of these techniques are now going to find their way into traditional enterprise applications. Different story. Internet of Things means, this story of your refrigerator talking to your shopping list app on your phone saying, we are out of eggs. Now that you're in the grocery store, get some. This is not science fiction. Your thermometer can sense, these are commercially available today. Oh, there's no one in the house, drop the temperature. And mostly people come back around 5 o'clock, so let's crank it up again around 4 o'clock, so it's warm and toasty by the time they're back in. These are all very doable, right? It's only a matter of standardization, right? So that it can be done at scale and cost effectively enough for all of us to use, as opposed to just the geeks in Silicon Valley, right? It's simply a matter of the price curves coming down, and that's a matter of standardization. The numbers here are mind-boggling. In case you don't notice, by 2020, they're predicting there'll be 50 billion devices, right? The amount of traffic on the internet is going to be 275 exabytes per day. These are eye-poppingly large numbers. And all this data, what does it mean? We're able to observe data automatically, capture this data in ways we never could before. Prior to the internet generation, data entry was largely through keystrokes. The volume of useful data you can enter that way is minuscule, right? Now, data capture has become trivial and ubiquitous. Everything is observable, for better or worse. The cost of hardware has plummeted, and our technical ability to build scale-out analytic systems, which is what I'll talk about for the rest of the talk, means we can actually do useful things with all this data in domain after domain after domain. And that, I think, it's that confluence of things that's made this whole field explosive. Lastly, don't underestimate the power of the cloud. right? You can have all the technology in the world that lets you operate a farm of 10,000 servers. But if you need to buy those 10,000 servers and install them yourselves, you're going to be a long while doing it. The cloud takes away that last barrier. You can rent on demand, right? Someone else will run that farm for you. So with that setting the stage, let's move on. I'll skip this. Here's an example from Microsoft, actually. What does it mean to have an operating system for all the sensors that go into your house? How do we standardize this? As I said, standardization is the next frontier. Already, lots of people are thinking about this. It's going to happen. Okay? So what kind of an architecture do I envision all this will require? First, I think in contrast to traditional database systems, you can't have things siloed. Your analytics stores, your transactional stores, for analytics, many different kinds of backends. All this increases the barrier to use by a user. You're going to have a digital shoebox, or some people call it a pool or a lake, or whatever the metaphor you use. One place where you can put a diverse range of data, be it documents, be it multimedia, be it traditional relations, be it streams, be it graphs, right? And you can put any amount of data in the same place. It'll just expand and hold it. And not only hold it, allow you to retrieve efficiently. Okay? Second, that efficient part is going to push the frontier in terms of the technology. A lot of the scale out to date owes to work in parallel databases and work on parallel distributed file systems like GFS. And the intuition essentially is spray your data uniformly across a bazillion machines and then shard your computation accordingly. Break up your query, for example, into little tiny pieces on the shards of data that larger query touches. So if you scan a file and the file is on 1,000 machines, then your query becomes 1,000 little baby queries, each running on a shard of your data. Okay, that simple principle carried us a long way. But now, in addition to this spread, there is a depth. If you look at data that's on local disk, all the file systems we talk about essentially stop there. There are 3 copies on the local disks of 3 different machines. That's as far as the metadata in HDFS gets you. But now, whether something is in the local disk, or main memory, or SSD, or NVRAM, makes a huge difference. Not only performance-wise, these different forms of memory are becoming cheap enough. You can have scads of main memory, for example, loaded onto a machine. And if you don't make use of it wisely, you will not meet the performance criteria that you need on many of these applications. Furthermore, for inexpensive storage, you don't stop with a single machine, of course. You have remote storage. You have tape. You have all kinds of storage that's farther away, slower, but much cheaper. Right? This means if you really want to store everything at all without worrying about the cost, your buffer management becomes crucial. You're not going to see buffer management on steroids, very far to very near and across tens of thousands of machines. This is the challenge of tiered storage, right? And one last little detail. Historically, database buffer managers have been tied crucially to one class of workloads, SQL queries. Now, as I'll describe in a moment, you're going to have a plethora of analytics, from graph processing to streaming to machine learning to SQL queries. And you need a buffer manager that can take you a long distance towards all of these workloads. So as a database person, my cup floweth over. This is lifetime job security. Okay. Of course, however beautiful your store, people will always have good reasons for keeping their data in other places as well, maybe on-prem, maybe in some specialized store that they're locked into for whatever legacy reasons. It's up to us to make access, at least, maybe not every bit as efficient, but access, functional access, available to all data no matter where it is. Now, on top of it, from the end user's point of view, they care about many different programming paradigms. SQL is ubiquitous. If you take things like Hive, Peg, they're just variants of SQL in my opinion. Mapreduce has gained a lot of mind share. But let's stop for a moment and think about Mapreduce. How many of you know about Mapreduce already? Okay, great. So I can be really brief. Mapreduce is just SQL's group by. At a very surface level, that is indeed true, but there's a bit more to it. First, when you group the underlying rows in the group, if you preserve them as opposed to distilling them through an aggregate, that is the map step. And subsequently, within each group, rather than applying one of a predefined set of aggregates, if you could write arbitrary user code to run against a partition, that's reduce. So MapReduce and SQL group bys indeed are very similar. The language construct owes, of course, to lambda calculus. But if you take all of this, you're still missing the essential contribution in MapReduce, which I think are twofold. First, an enormous range of user code can be effectively parallelized in this manner. That's a deep insight, right? For the class of things people did at the web search companies, AltaVista, Bing, Inktomi, right? This was well known. The genius of the MapReduce abstraction was to make it broadly available. The second step, when you parallelize at the scale of thousands of servers, traditional database systems didn't go above tens, right? The scheme of restarting when any one part failed is not good enough. You have to plan for failure. So failure-centric architectures were the other big contribution of MapReduce systems. But language-wise today, MapReduce is folded into SQL extensions like Hive or Pig, or here in Microsoft, something called Scope. Okay? And if you look at the statistics, 95–98% of all MapReduce queries at Facebook, at Yahoo, they're really Hive queries or Pig queries that have been translated into MapReduce. So end users using MapReduce is a vanishingly small case, right? The revolution has been somewhat different. But those 2 or 3% where you still have to default to MapReduce do turn out to be significant, which is why all of these languages support essentially MapReduce in slightly different syntax. Okay, coming back, stream processing. Real-time analytics is now again becoming mainstream. Things like roll-up, drill-down, BI. It's a $2 billion business for Microsoft alone, right? As a market, it's much bigger. Machine learning is growing explosively, right? When you have so much data, everyone kind of understands, hey, human analysis, manual analysis can't cover all of it. What can we teach machines to look for on their own? If you take this diversity of analytics over all the variety of data that you expect to store here, the underlying computational substrate, how do you build it? Are you going to build a different stack for SQL, for stream processing, for machine learning? Or can you share some steps in between, right? This compute fabric is an area where there's a lot of research going on today, okay? And I'll say a little bit more about it. And this is, when you look at virtually any big data player today, you'll see some variant of this slide in how they think about the space. Okay, this is not unique to us. So here's a link actually. Where you can go look at what many people are doing in this space. All right. In the second half of this talk, I'll talk a little bit more about that compute fabric. And essentially, here's the question I'll try and address. Given that there's enormous amounts of very diverse data being analyzed in a single application, mind you, right, at different stages in the pipeline. I use SQL, I use machine learning, I use streaming systems, I use graph analytics. What's the system underneath? Am I going to see a single SQL box that all of a sudden does streaming, does machine learning, does this, does that, everything? Or am I going to see a whole federation of systems built completely standalone, which I mix and match on my own dime? I think either of these is unrealistic. The first will simply not allow for the agility that we see here in this space. And the systems will simply not be usable, right? SQL by itself was being criticized for having everything but the kitchen sink. When you take all of these other things and slap them all together, it's unmanageable. The second alternative, go ahead and build your stacks by yourselves in each domain, in each type of analytics, and let the end users figure out how to mix and match. End users will not, they cannot, right? You need to make interoperability across, say, SQL and machine learning a first-class design consideration and make the edges seamless. That means the underlying computation fabric needs to satisfy some criteria. The intermediate computation in a SQL query must be something you can pipeline to a Mapreduce step, for example. The iterations in machine learning, you must be able to seamlessly pass along. So these kinds of considerations, where do they lead us? What I think is going to happen is an evolution of what we are already seeing in Hadoop with Yarn. How many of you have heard of Yarn or Mesos? Okay, fewer people. So let me speak briefly about this. If you take Mapreduce, the original implementation of Mapreduce in Hadoop, which was an open source implementation of the GFS Mapreduce stack from Google, Hadoop was largely done at Yahoo. The original implementation of Mapreduce was monolithic, right? The programming paradigm of Mapreduce, the implementation, all the way down to the bare metal, it was one composite thing. Then along came Pig, which was Yahoo's variant of SQL. In parallel, there was Hive, which was Facebook's version of the same thing. These higher level languages, they had a choice. Do we implement them from scratch? Oh boy, it's going to take a lot of effort, right? Why don't we just translate Pig queries into Mapreduce programs? That was the original implementation approach. They simply translated and then executed the translated program. Now, there was a price here. If you take a Pig program and translate it into Mapreduce and stare at the same Pig program and as a human being, rewrite that in Mapreduce from scratch, the difference between these was, I don't know, in the original days, easily over a factor of 10 in performance. Today, it's still a non-trivial tax you pay, not as big. It didn't matter, right? As I told you, from the very earliest days, people started using these higher level languages more than Mapreduce. To the point where today the usage is in the high 90% of Mapreduce programs being translations. Which led to the obvious question, maybe we should think about implementing languages like Pig and Hive natively. Then again, do we need to start from scratch? Are there things that are common? Yes, there are. So think about how these programs work. A user submits a job. You know that the job is going to be broken up into baby jobs running against parts of the data. To do so, you're going to have to go to the underlying cluster and say, hey, give me compute containers with some constraints. So let's take a very simple example. I want to scan a very large file and count the average of some column in that file, right? So my data is broken up across 1,000 machines. And what I'm going to go and say is, hey, give me 1,000 slots on each of these 1,000 machines. So each slot I can use to compute the local aggregate, and then I'll sum them all up. So first, you go negotiate, you get the resources, then you install the particular executable for your query in each of these 1,000 slots, and then off you go. What you put into those 1,000 slots is specific to this particular query, more generally to SQL. The SQL engine is something that does this. But the actual negotiation with some owner of the underlying resources, this is common. This realization led to resource managers like Yarn, which was the Yahoo version, Mesos, the Berkeley version, Corona, the Facebook version, Omega, the Google version. I mean, there's a pattern here, right? Everyone saw the same writing on the wall. And the net of it is, now the resource managers form a common substrate. No one has to do resource management separately. They sit on top, get their resources, from there on they do their own thing. Okay? This also provides some other advantages. If you have a multi-tenanted cluster, priority can be set by whose needs are most important, regardless of whether they're issuing a SQL query or a machine learning query. You can interleave very different types of computation. You can have heterogeneous job pipelines all executing on the same cluster. There is no notion of these machines do only SQL, those machines do only machine learning, right? Lots of things fall out. Okay, so that's resource management. Let's talk about yarn very, very briefly. I've said some of this already, right? Multiple kinds of engines can share the same pool, and I'll use the word container or slot interchangeably, right? If you take this, the underlying algorithms for scheduling, deciding whether Tony's request trumps Raghu's request, it should, of course. There's a lot of research, okay? Now, I need to have a technical slide here. Come on, I'm not wearing a coat. So here's an example of some work that we actually did on preemption. And I'm just going to give you a brief feel for this. It'll also help me illustrate some of what goes on in Mapreduce. So in Mapreduce, it works in waves. First, you take your data, you partition it in a way that's appropriate to your problem using the map step. The mappers all execute as independent tasks. When they are done, the reducers come along and take each partition and do something else. And what you're left with is a collection of partial results which you sum together and you get your final result. Let's look at this graphically. Here are the mappers. Each line is, there's a mapper that starts here and ends only here. This mapper begins, ends, and so on. These are all mappers. Each row here is a particular machine and what's going on that machine, okay? This, of course, is time. These are stragglers. It's well known that the tail of map jobs in a map phase have a huge impact on overall performance. Let's see why. In standard Mapreduce, in all of these systems, by the way, to begin with, preemption was not part of the story. So once you allocate a slot to a task, you simply wait till the bitter end until the task completes and returns the slot to you. So in that regime, let's see what happens. You allocate all these slots to the map steps of a job. They're all going to go on. Some of these finish before others. So you can reuse some of those slots, right? So some of these rows are overlaid on some of these rows, okay? In fact, on some of these machines. The reduce step starts. But now, somewhere here, let's say, those reducers get blocked because they're waiting for the straggler to compute. Remember, in a group by, if you're consuming the result, you need to be sure your group is complete. When you get there, you hit a hard wall. In sorting, the exact same story. You guys know what I'm talking about. So here, these machines lie fallow. Why? The choice is to nuke all these jobs and start over, which they do sometimes. It has its own consequences. Or you just wait to be unblocked. When finally the straggler completes, you can resume. And then the remaining reducers are scheduled as well, and the job eventually completes. Now, this red area starkly illustrates the impact of a straggler in the absence of preemption. Okay, so you kind of begin to see the subtleties under the covers. Okay. Now, let's look at this option instead. If you could preempt, if you could say at this point, save the state efficiently and use these machines to do something else because you're blocked on these particular tasks, what could you do, right? If you were to do this, you could continue, you could get some of the other reducers going on the same physical machines here, right? Those, I wish I were Nordic. In that case, I wouldn't have to use this. But here, if you look at these reducers, they're running on these machines which have now been paused on these reduced tasks. You get what I'm saying? And therefore, instead of sitting on your fanny, you could actually be doing some useful stuff, which means the whole thing completes sooner. Okay? This is under the assumption that you can efficiently checkpoint the work done by these guys. So you need a checkpoint mechanism. But if you had that, you get a significant improvement in performance, right? This is the kind of stuff that's going on as we speak. These systems, for all the impressive characteristics, there's a lot of traditional stuff that they need to incorporate, let alone break some new ground in many ways. So this particular scenario, we showed it had a 1/3 improvement. All I want to say in the next few slides is, you know what, all of this work, we actually contributed to Hadoop open source, Apache open source. Here are the JIRAs for those of you who are interested. This is just to kind of make the point, Microsoft is serious about giving back to open source. So we are very much involved in Hadoop, both as a consumer. We offer a product called HD Insight, which is similar to EMR, right? So we consume from open source, and as you saw in this example, we also give back. In fact, several of the people on the Hadoop Council committers, they work at Microsoft. All right, switching gears now. I've taken you all the way through Yarn. What next? Well, let's follow the thread. I now want to use Yarn or a resource manager like Yarn to build SQL, to build machine learning. Have I gotten everything in common that I could? From here on, do I have to build custom versions of each stack? Hopefully not. So the Reef project was an attempt to push the common substrate one level higher. There are a lot of things. For example, if I have 1,000 tasks, which of them died, just monitoring them can be a chore. Restarting automatically can be a chore. Checkpointing can be a chore. How many of these things can you package into a collection of libraries that are common? What are the further, deeper benefits of doing this? That's what the Reef story is about, and I'll try and walk you through that. Okay. Again, this is a Microsoft project done in Sizzle, now going on in the big data team as well, and again, we have open sourced it through Apache. So let's take a concrete example of machine learning. User activity modeling. You want to find out what a particular user likes. Okay? And you infer this by looking at the pages they browsed, the queries they asked, and the ads they ignored or clicked. Mostly people ignore ads. If you look at the number of pages per user, a few tens, the number of possible pages there are on a typical website, millions, right? The number of queries that users collectively ask, hundreds of millions. What they actually ask any given user, relatively few. The point being, these are highly sparse, but these are the observations you have to work with. How do you learn from this? Imagine this time window in which the user's activity is overlaid, and you gather this from various kinds of logs, web logs or search logs. And in any given window, you look at the things that you can observe. Oh, the user just issued this kind of query or visited this kind of website. Based on that, what are they going to do next? That is the crucial question. This is what user activity modeling is going to provide for you. Features that, given this, will allow you to predict this. Okay? So if someone visits finance and issues a query about the stock market, chances are good they'll sign up for E-Trade. Okay? I mean, I'm oversimplifying, but you get the idea. How do you build such models? You take your logs and slide this window step by step, and each slide of the window, right, gives you a case to learn from. So the very first step is to gather all these logs, clean them up, deal with things like robot clicks and winnow them out of the way, and then slide, 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 each time extract a row in your training database. This is a ginormous task, okay? And it is preparatory to any kind of modeling. Okay, and if you look at the times involved, acquiring the data takes several hours. These are somewhat old Yahoo numbers, but you'll see very similar numbers from Bing or from Google. Feature and target generation, right? Roughly, each window, feature window, has about 1 terabyte. This work, extracting the cases, takes about 4 to 6 hours. The actual model training, what we write papers about, this takes 1 to 2 hours. and not just for a single model. While you're at it, you may as well build hundreds of models, okay, because you're going to evaluate them all through bucket tests. Just think about this for a moment. When you think about the nexus between big data and analytics or machine learning, this slide is something that should be burned into your soul. Okay? Machine learning academically is all about the algorithms. Machine learning for real is all about the plumbing. Right? And this is why having your scalable data management systems be seamlessly integrated with your machine learning frameworks is crucial. Okay. Let's look at this in a bit more detail. One of the things I looked at Yahoo was phishing, mail spam, and the like. So here's an example about a spam filter. You have your inbox, and the algorithms, the spam filters, try to take a given user's mail and fork them into real mail and spam. Okay? The user actually sees this through the mail front end. Okay? Occasionally you screw up. You take spam and put it in the inbox. Even more occasionally someone will complain. They'll mark that as spam. And that's your signal to learn from. Okay. Now let's fast forward. What does it take to learn from that? You need example formation, modeling, evaluation, the same cycle you saw earlier, right? And if you look at this, I'll start moving a little bit faster here. The example formation can really be done reasonably efficiently using systems like Hadoop. It's really a gigantic join between the mailbox and the spam signals. You can do this well. Hadoop helps you do this well. Okay? If you take the modeling step, different story. Modeling is not so easy. Okay? Modeling is massively iterative, and Mapreduce doesn't really support iteration. In between iterations, you need to write to disk. So nowadays, you have seen things like Spark and Shark that try to keep things in memory to avoid writing to disk in between iterations. Okay? The good news is Mapreduce supports one of the basic models for machine learning, the statistical query model of Michael Kearns, pretty well. Other models, they don't map so well to Mapreduce. Okay? Net of it, this iterative cycle, even a single model is iterative, but there's an outer loop. Apply a model, observe errors, update it, try again, do different kinds of features, try again. This whole iterative cycle is not well supported in Mapreduce. Okay? So, going a little bit faster, net of it is what I just told you. It can be used, but not easily, not efficiently. What has this led to? People cheat. People are infinitely creative. They use map-only jobs, no reduced step. What the heck is going on here? They're essentially getting threads from a ginormous thread pool and having a party. Okay? You can do anything you want. Just give me the resources and get out of my way. But if you do this, I hate animations. Okay. These are examples. For those of you familiar with machine learning, there are things like all-reduce and decision trees, which all superimpose a complex communication structure across many tasks. You code this on your own. Each of these is a map-only task. You establish your own communication channels. If one of those boxes dies, you're in doo-doo. You deal with it. All of these things that Mapreduce supposedly gave you as part of the framework, you do all over again because you're abusing the system to make it jump through hoops it wasn't designed to. Okay? So, all said, let me cut to the chase here. Yeah, I can go on through more and more of these examples. All this leads to unhappiness on both sides. The people who do this kind of abuse, not because they want to be abusers, because they don't have options. They have a fault tolerance mismatch, so they have to redo fault tolerance or live without it. The resource model they're just building their own. There's no notion of a tree, for example. Their integration with Mapreduce essentially is to treat them as map-only jobs. They have to deal with networking, cluster memberships, bulk data transfers, pretty much all of the work. For the cluster, life is not so great. For example, the network usage patterns in these kinds of applications are very different. This leads to problems. Another, consider what happens when you need, say, gang scheduling. If you need a collection of nodes to be given to you in order to proceed, this happens, for example, in Giraffe, the graph processing system. What does Giraffe do? It gets resources one by one from the underlying resource manager until it has enough. Meantime, it squats on the resources it has. This means the utilization of the system tanks. Everyone else is affected because you have given someone resources piecemeal when what their requirement is an all or nothing, give me at least 100, right? So how do you deal with all of this? What you really need is this intermediate stage that complements Yarn, right, to facilitate development of applications on top of Yarn and lets you build pipelines of these different kinds of computations. So let me illustrate this with a concrete example and then I'll conclude. In this example, the job driver, it's really the control in the example program. Activity, it's the user code. This is what you would execute in a Mapreduce task, your actual code running there. Evaluator is simply the container. It's a Reef term just saying it's a Reef controlled evaluator. Okay? With this, let's consider the simplest of tasks. Let's say you want to do distributed shell. Run the same command on two different machines. Here's what would happen in a scenario with Reef. You want to run this command. You would first come to a cluster that knows about Hadoop, Yarn, Reef, all of these things. And when you come in, the client is, your client executing, trying to do distributed shell. You submit your job. The first thing that's going to happen is you will launch a Reef container on one of the machines. The very first thing that Reef container will do is to launch the special program called the job driver, which includes your code to orchestrate the logic of your program. The job driver now negotiates on behalf of the job, right, with the resource manager. The negotiation results in tokens it can use to create tasks. It'll get containers through the resource manager, and on these, it'll install some libraries, it'll install the actual user code, right, your task, and it's able to run this task on this machine. Imagine the same thing happening on all the other machines in parallel. Okay? Now your command is running on these two machines. And instead of running dir, you could be running anything at all you wanted across these two machines, right? Or 20,000 machines for that matter. These are going to communicate with the job driver through a regular heart beating mechanism, which primarily allows the job driver to take over the mundane task of babysitting these bazillion tasks, restarting them should one of them fail. And the restart may happen on a different machine, because if a task fails, the job driver will detect this, go back to the resource manager, get another container, restart that activity. If you want the state that was lost to be available, you will explicitly use one of the checkpoint commands to save the state durably across machines, and that will then be available when the job is restarted. So in a nutshell, these are all capabilities that make it possible to write, say, a SQL engine, or a new implementation of Giraffe, or a new implementation of a machine learning algorithm at scale. One last thing, and this is a really, really important thing. Okay, let me get past the here. So let's say this particular task completes. You still have the evaluator. So Reef essentially acts as the middleman between you and the cluster manager. And when you complete one of the tasks you have installed in a container, you have the opportunity to install a follow-up task. So think iterations in machine learning. After one iteration completes, your container is available with metadata about what state you have left over from that iteration. You can install the code for the next iteration. The data never goes to disk and comes back. You're iterating in main memory. This by itself, either doing this or running in something like Spark, gives you a 30x improvement in performance. Okay? Now, when you pull all this together, what you effectively have is the reef system. In the interest of time, speaking of checkpoints, I'm going to checkpoint right here. Okay? For those of you familiar with RX, there's a lot of similarity with RX in the underlying APIs. Net, if you're interested, all of this is available through GitHub. Send me or Dennis a mail and we'll send you a link. So let me pause here. Today, the main message I want you to take away. Over the next 5 years, everything is going to revolve around data. The kind of data is diverse, right? It could be data that's very specific to what you're doing. But what is universal is our world is becoming data-driven. And this is going to require us to develop systems to manage data of a diversity and a scale that's unprecedented, and to provide analytic tools. Here's one other point. If everything is data-driven, a corollary is domain scientists who care about the domain science, not learning ever-increasing complicated versions of SQL and this and that, are going to be using these systems. That means you need to build domain-specific languages. You're going to see a plethora of analytics is my guess. So having the kitchen sink is not an option. Having many tailored systems. If that's where you're going, these tailored systems inevitably will have to do some part of their work in concert with other systems, right? Everyone, for example, will have to live with SQL, right? How do you support these kinds of diverse analytic engines on top of a common compute fabric, a common caching capability, a common distribution, checkpointing, fault tolerance, right? All the major players are thinking about this. In the cloud, Google, Amazon, Microsoft, they're all in the game. It's a fun time to be working on this kind of stuff. So I'll pause there.
Let's thank Raghu.